Welcome back to this second lecture on group equivariant deep learning. In this particular lecture we're going to focus on a class of group convolutions called steerable group convolutions. And this is a class of group convolution methods that has some very nice properties and are very convenient to work with, as we will see in the upcoming videos. And central to this notion of steerable group convolutions is this idea or this notion of steerable kernels or steerable basis functions. So that's what we're going to cover first. And throughout the upcoming videos, I will mainly focus on the SO2, so the 2D rotation case. And then in lecture 3, so the next lecture, we will see a bit more examples of steerable methods in the 3D setting. But the 2D case is nice to get the intuition right. Before we get there, let's go again over an overview how this lecture is split. So we're going to start off with the definition of steerable kernels or steerable basis functions. And then once we have an idea of what steerable kernels are and how to work with them, we're going to see what it looks like if we were to apply them in regular group convolutions. And this will get the intuition right for the steerable group convolutional network, but it doesn't explain yet the full framework. In order to do that, we need to learn a little bit more about group theory. So we have 2 short videos on irreducible representations and how it relates to a Fourier transform on groups. And 2.4, again, a little bit more of theory. Talking again about representations, and this time about induced representations, which is a relevant definition when working with feature fields, such as vector fields, where also the codomain transforms in a particular way. And once that is done, we have everything in place to talk about steerable group convolutional neural networks. And so we'll learn a bit what they are and how to use them as well. In particular, in lecture 2.6, I will talk a bit more about the types of activation functions that you can use for these CNNs and a bit general design of these neural networks covered in 5 and 6 together. And finally, I want to recall that these steerable group convolutions are really also just linear operators that are equivariant, and hence they are a class of group convolutions. That's what we learned in the last video, that every linear equivariant operator is a group convolutions. And when reading these steerable convolution papers, it's not really apparent at first sight that they are group convolutions. So I'm going to make this very explicit to pick an example. So we're really going to derive harmonic network, which is really, I think, a classic paper, one of the first steerable neural network papers out there, and show that they indeed correspond to regular group convolutions. Okay, so let's go over this definition. So we use this notation that y of x is really a vector of the basis function values evaluated at location x. Now, we call such a vector a steerable vector of basis function if a transformation achieved through a warping or transformation on the domain can also be achieved simply by taking a linear combination of these basis functions themselves. So that really means that a transformation of these functions keeps the entire set of basis functions intact, right? So I can either transform the domain of these functions, resample, or I can simply reshuffle or take linear combinations of these basis functions and take a look at that vector. Okay, and I'll of course illustrate this in the upcoming slide with some visuals. But the idea here is that we are again talking about group theory, because this needs to hold for all elements in the group. This is what you can see as the group G acting on the domain X of these functions, and this rho G now acts on L-dimensional vectors. And since this holds for all groups, all group elements, rho of G is really a representation of the group G. Okay, so let's have a look at a certain class of basis functions called circular harmonics. So now we're considering functions on the ring, and we can expand them in these complex exponentials. And these functions are steered via representations that have actually the same form. So this is of course not really a coincidence, right? Because we know that multiplication of these representations can be described with a single representation with a shift in its argument. And okay, let's just go over this example, a very simple proof that this is indeed a steerable basis function. So we have a base function alpha shifted by y of alpha shifted by an amount of theta. So this is actually the negative group action taking place over here. Okay, so let's fill that in. That's e to the power il alpha minus theta. This exponential splits. So we see our original basis function over here and the row of the representation of the inverse group element at the front. So this is precisely the definition of steerability that we saw over here. It's just that now we applied the inverse group element, and that leads to an inverse action of the representation on the set of on our basis function. Okay, so what does that look like? Suppose we have a basis function, which is a complex exponential. What I'm showing over here is its real part. It's this cosine. And we have the imaginary part, which is really just the sine of the same frequency. And if I multiply this complex basis function with this e to the power minus I theta, this induces a shift over here. So I'm not doing anything to the arguments of these functions. I'm just multiplying its codomain with some complex number, and that induces this particular shift that you see over here. Okay, so we have this entire set of basis functions, e to the power il alpha, where alpha is an element on the ring, and each of these basis functions are identified with a particular frequency. And this is actually a very known class of basis function called circular harmonics, or the Fourier basis on the ring. And it has the very nice property that it forms a complete set of basis functions for any functions on an L2 S1, meaning that any function on this ring can be expressed as a linear sum or linear combination of these basis functions. In the limit to infinity, I can represent any function I want. So every basis function gets a particular weight, which we're going to put in front of here. I'm going to denote these weights with a hat. So a hat refers to something to do with the Fourier transform. And I'm putting this overline, the conjugate, the complex conjugate over there, because that draws the connection between the inverse Fourier transform. This expression should be considered an inverse Fourier transform, meaning we recover the signal f alpha from the Fourier coefficients via this expression. And I might as well put this bar over there, over the basis functions, which means I reflect the basis function. And maybe now you see a bit more the parallel with the regular definition of Fourier transform, if you have seen that before. But even if you haven't seen that before, it doesn't matter. I'm going to use this notation, and still the same properties hold, that I can represent any signal as a linear combination of this set of basis function with corresponding weights. And now there's actually a lot of interesting group theory involved over here. For example, the completeness of this Fourier basis follows from Peter Weil theorem, which we're not going to cover in these lectures. We're mainly going to focus on intuition and practical applicability of these steerable methods. So for now, it's really sufficient to know that, okay, we can represent signals as a sum of these basis functions. And that looks something like this. Suppose I have a very sharp function on the sphere, right? From 0 to 2 pi, or on the ring, I mean, from 0 to 2 pi, this sort of sawtooth signal, right? So I can actually represent it as a sum of these sines and cosines that are part of these complex exponentials. So if I only take the 0th order frequency, the first frequency, this is really the best fit I can make. But then if I increase the number of frequencies, you see that I can find weights W such that I'm really approximating the signal quite well, even these sharp transitions. And in the limit, when this band limit goes to infinitely, I'm precisely able to reproduce this original signal. Okay, so let's go back to this steerability condition. So we just talked about individual basis functions and how they transform. And obviously, if I now have a set of these basis functions, so I can stack them on top of each other, then this collection of basis functions transforms, well, element-wise, right? Because each individual basis function could be steered by just multiplying it with a complex number. So I can represent this transformed set of basis functions, so the shifted set of basis functions, by this diagonal matrix, which multiplies the corresponding representation with the corresponding basis function. And we're often going to use this notation where this tensor sum notation denotes the formation of this block diagonal matrix, where along the diagonal we have these blocks of representations, rho L. And in general, these blocks can be small matrices themselves, but now these complex numbers can be thought of as 1 by 1 complex valued representation matrices. And if we then take this tensor sum of these 1 by 1 matrices, we create this big diagonal matrix which represents the entire group on this for this vector of basis functions. Later on we will see an example where these rho L's are actually matrices. Okay, so what does this all tell us? It tells us that we can represent any function in these circular harmonics by finding the correct Fourier coefficients. And the expansion of these functions in these circular harmonics is here denoted in vector multiplication, right? So I have a vector of weights, I take the conjugate transpose, multiply with this vector of a basis function, and that's summing all these basis functions with the corresponding weights, right? And then if we do this, then we can see that such functions are clearly steerable by simply transforming the weights. So if I shift this function by an amount of theta, I might as well let the representation act on the weights on the left. So I keep the set of basis functions the same. I just, update the weights, and this updated weight then represents a shift of the function as indicated over here. All right, so that's summarized over here. So I can expand any such function in a circular harmonics up to some frequency. And once I've done that, I can shift it by simply manipulating its weights. And I put a simple proof over here for reference, which you could maybe look into later on. Okay, now we want to use this representation theory and this idea of steerable functions to images to build group convolutional neural networks with them, for example. So what I just covered is that these rho L's e to the power I L theta are representations of SO2 acting on complex numbers. But ideally we want now to work with this function space R2, right? With 2D images, let's say. And we already saw in the previous lecture that this group SO2 does not act transitively on R2, which sometimes complicates things a bit. But in this case, actually not necessarily, because we just saw that SO2 does act transitively on S1. So on these rings, on these orbits of SO2 in the plane, we have this representation working. So what we could do, we can glue all these rings together with, let's say, an index that indexes the distance to the origin, and then treat them all separately or glue them together with some radial function. And that's what we're going to do. So we're going to not use regular coordinates in R2, but we're going to use polar coordinates. So we can equally describe a position in 2D plane via a radial coordinate and an angular coordinate, right? So a distance and an angle relative to the x-axis, let's say. And we do that, of course, because now we can focus on this angular part of these polar coordinates. So we can use the representation theory of SO2, which we just saw for the ring, and the distance, of course, distances are preserved for all these rotations. So this part stays invariant in the rotation. So this is what we're going to do. We're looking at 2D functions, could be a convolution kernel, for example, and we're going to describe it in polar coordinates, right? So not just in an x1 and x2 coordinate, but in a radius, or distance to the origin, and an angle, where we have this relation for polar coordinates. Okay, and then in these polar coordinates, we also have an action of SO2, where in the regular case it's just a matrix vector multiplication, and now in these polar coordinates you will see that the radius stays unaffected by a rotation, but well, the angle of course is shifted by an amount of theta. And that is again a very easy derivation using these rules for cosine and sine multiplication. Please check them out in your own time. And so what we have is that then functions are simply transformed by a shift along the angular axis, right? Where here we have the regular representation on these functions, are obtained by a shift, a transformation of the domain by the inverse rotation matrix. Here we have that the regular representation transforms these functions simply by a shift in this alpha or angle axis. And now what we're going to do is we're going to make a polar separable convolution kernels and focus on the angular part. Where this separability means is that I have in principle a function on r and theta, and I'm going to split this into the product of one part that only depends on the radius, another part that only depends on the angle. And we do that, of course, because now we have a function on S1, so we can conveniently pick a steerable basis for this part of the function. And for R, we can pick basically any other function that depends on the radius we want. And that is illustrated over here. So for the angular part, we pick, for example, these circular harmonics. And for the radial part, it could be these B-splines, which I'm going to show in the next slide. And then the product of this radial function and the angular function jointly gives us a function, a 2D function, right, on the 2D plane. And that looks something like this. So we have this whole collection of basis functions, which we're going to use to expand convolution kernels in. Okay, so a quick summary. So we have our spatial convolution kernel parameterized with a bunch of weights, and we're going to split this into a part that only depends on the radius and a part that only depends on alpha. And each of these two functions is parameterized by its own weights, let's say. So the angular part we're going to expand in circular harmonics as a function of alpha, right? So this 2D plane, every pixel has its own angle that it makes with the x-axis, and so we can evaluate this alpha in these circular harmonics, and that gives us functions like this. And then for the radial part, we can also pick some convenient basis function. But here we're not going to do anything with steerability. Steerability only now focuses on this rotation part. But what I did over here, I picked B-splines, which is a convenient type of basis functions, which look a bit like this. So these are my basis functions. They sort of look like smoothed out pixels, equally spaced. And yeah, that's I think how you should think of them. And also here we have that if we increase the resolution or the number of basis functions, we can start representing more and more complex function and add more and more detail along this radial axis. So given enough radial basis functions, we can also represent any function on this axis that we want. Okay, and now let's just write out this kernel. So this kernel is a product of these two functions, which are both a sum over their basis functions. So, okay, let's do that. So we have the weights of the radial and the angular basis functions, which we can basically collect together. If these are learnable parameters, we might as well pick one learnable parameter index with an M and an L. And to make the whole steerable aspect a bit more obvious, we're going to group this together, and we're going to treat this product of these weights with these radial basis functions as weights that depend on a radius parameter. So we're really saying that our spherical harmonic weights or circular harmonic weights depend on the radius in this particular way. And we're writing it here in this form because then we're back to where we started off with these steerable functions, that if I have such a steerable function and I rotate it by r theta, then I simply transform its weights, which could still depend on the radius. So yeah, what we did here, we expanded these radius dependent weights into a basis of B-splines. But what we see a lot in literature is that these weights are simply parameterized by an MLP in itself. So this multi-layer perceptron takes as input a radius value or a distance r and just spits out a weight or a weight matrix, a weight vector, which we then use to expand our kernel in these spherical harmonics or circular harmonics. I think we will see some examples of this approach in lecture 3 when we talk about 3D steerable methods. Okay, so let's get back again to the steerable basis function. So, well, I might as well ask this radius depending mask on it, which is invariant to rotations. It doesn't matter much, so we focus now here on these angular basis functions. So we see that these are functions as a function of alpha, you might say, which transform again via multiplication with these complex numbers. And what is worth noting here is that in practice we often work with real valued functions, and we don't want to go through the hassle of working with complex functions. And it's really like these functions that you see over here, it's like depending on the cosine of the alpha and the sine of the alpha parameter. So what we could do, we could just take the real and imaginary part, stack them on top of each other, and that looks something like this. So we multiply the real part of a representation with the real part of y. We multiply the imaginary part of our complex representation with the imaginary part of y, and then the same for the imaginary part of a representation with the real part, and so on. So these combinations are really encoded in this matrix vector multiplication. So this thing together is the equivalent of our complex representation. So this one over here is equivalent to this rho L theta is e to the power minus I L theta that we saw before, but this is its real valued equivalent. So what we see now is that along this diagonal we have matrix valued representations. And what we also see that each of these representation acts on a subspace of these basis functions, right? So we have these two-dimensional vector subspaces, which are all affected by their own corresponding representation, and that creates this block diagonal form that you see over here. Okay, now the main take-home message of this first video is that basically we can represent any function in such a set of basis functions, where the exercise would be, or we can leave this to our neural networks, of course, to find these weights, but the exercise would be to tune the weights until you start seeing something interesting or useful. And as a hyperparameter, we can increase the frequencies to add more and more details, right? Until we see something different, so something interesting, like this, of course, and then we're going to use it for template matching or whatever application we need. So we're going to use these kernels in a neural network. And to do that, especially in group convolutions, we need to start rotating these convolution kernels. And now we can simply do that by transforming the weights. And this has some very nice implications, some results that we can build on. And that's what we're going to do in the next videos.